Welcome back to part 3 of chapter 7. So far we have balanced equations and looked at the coefficients which relate the number of moles of a chemical to the number of moles of another chemical, right? And such as the moles of silicon tetrachloride to moles of silicon dioxide, which is a one-to-one relationship. So and then we practiced a whole bunch of mole-to-mole conversions, mole A to mole B, or mole B to mole C, mole D to mole A, and so on and so forth. And we also know the simple conversion factors based on the molecular weight, which is of course 1 mole of, let's say, nickel is equal to 58.69 grams. That's a number that comes straight from the periodic table. So we know how to relate the number of moles to the number of grams of a particular reagent or a chemical, and vice versa. And most of the times we're going to be asking, if I have, let's say, 100 grams of a reactants, how many grams of a product can I produce, right? So if I have 100 grams of silicon tetrachloride, how many grams of silicon dioxide can I produce? So we don't have a conversion factor that relates the grams of one reagent to the grams of a second reagent. So we have to go through a 3-step conversion, as demonstrated here by this fudge factory down here, right? So if I'm given the moles of A, I have to if I'm given grams of A, I have to first convert grams of A to moles of A. Then I can use the coefficients from the balanced equation to convert to convert moles to moles, and then finally I go from moles of the second chemical to the moles to the grams of the second chemical here, right? So grams of A to grams of B is going to be a 3-step conversion. Right. Moles to moles is a 1-step conversion. You can have grams to moles, which is a 2-step conversion, or moles to grams, which is also a 2-step conversion. So in a way, you can use this scheme for all conversions. However, it's much easier to just simply think of it as vector dimensional analysis, that if you write your units and you always multiply and divide, right, where this is set up like this, right, grams of A, and then you set it up like this in these 3 steps, right, where you have moles of A divided by grams of A, and then moles of B divided by moles of A. That's exactly what this is here. And then finally go to grams of B divided by moles of B, so that your units are always canceling, and that you end up with the units that you're after, that you're asked for. Okay, so let's practice a few of these. For example, if I ask you this question, how many grams of hydrochloric acid would produce from 5.69 grams of silicon tetrachloride? So here we have silicon tetrachloride that we want to convert to hydrochloric acid. And so as we know already, we have a conversion factor that's 1 mole of HCl. Sorry, that's 4 equals 1 mole of SiCl4. But we don't need that. We can't deal with that because our units are not moles. What we're given is grams of silicon tetrachloride, right? So we have 5.69 grams of SiCl4. And so my first conversion has to be from grams to moles. And the relationship that is from the periodic table, the molecular weight. And the molecular weight of silicon tetrachloride is 169.898 grams of silicon tetrachloride. That's equal to 1 mole of silicon tetrachloride. So we do that as our first step. 1 mole of SiCl4 divided by 169.898 grams of SiCl4. Now our units are in moles. Grams of silicon chloride cancel, so now we can use this conversion factor. So times, and we have to multiply by 4 moles of HCl and divide by 1 mole of SiCl4. Again, you're just canceling units here. Moles cancels, silicon tetrachloride cancels. And since I'm asking for grams of HCl, I'm still not done. And the molecular weight of HCl is 36.461 grams for 1 mole here, right? And so that's our next conversion factor. 36.46 grams of HCl are equal to 1 mole of HCl. So then that cancels, and our units are in grams of HCl, and that is equal to 4.88 grams of HCl. So the answer here is 4.88 grams. This is it worked out again. Based on the same reaction, we have a different question here. How many grams of water, so grams of water is what I want, would react with 0.3756 grams of silicon tetrachloride? Okay, water and silicon tetrachloride. Those are the two we're looking for. You start out with grams here. 0.3756 grams of SiCl4. We know the molecular weight of silicon tetrachloride. We looked that up already. That's so times 1 mole of SiCl4 divided by 169.898 grams of SiCl4, just like we did before. But now we need to take the moles here, right? 1 mole. No matter what we do here, the only thing we can do is divide by something 1 mole of silicon tetrachloride. And then we need to find out what goes here. And that's, of course, the mole-to-mole relationship between water and silicon tetrachloride. 2 moles of H2O. And finally, so that cancels that. This was already canceled earlier. And finally, we go to the grams, and so there are 18.01 grams of water in 1 mole of water. And we end up with 0.07656 grams of water. So we're going to work a few more like that, okay? This is just cleaner again, like I told you. It shows nicely each step and how the units are canceling. And so we can work some more. Again, how many grams of CO2 would be produced from 9.27 grams of C4H10? So this is grams to grams. It's going to be a gram to gram conversion. We have butane and we have carbon dioxide. So let's look at the periodic table real quick and figure out what the molecular weights are of each of these. So 44.0098 grams of CO2 equals 1 mole of CO2, and butane is 58.123 grams, right? So those are the conversion factors, grams to moles and moles to grams. This will convert, we'll use that conversion factor to convert grams of moles. So that'll be step 1, 9.27 grams of C4H10 times 1 mole of C4H10 divided by that 58.123 grams of C4H10. And the next step is then, of course, the moles of carbon dioxide to the moles of butane. So we have 8 comes from here, moles of C CO2 divided by 2 moles of C4H10. And then finally, since I'm asking for grams, I'm going to use this times 44.0098 grams of CO2 divided by 1 mole of CO2. I'm going to write it down here, equals 28.1 gram of CO2. That's the answer to this question. And I encourage you to work these problems, to go ahead and pause and work these problems and then watch my lecture. That might even be the best, right? This is just the result. So what I'm saying is, here you go. Here's another question. Pause it, work it out, and then see if you got it right. How many grams of oxygen would react with 42.76 grams of butane? Well, we already determined that butane has a molecular weight of 58.123 grams, right? So we have butane here, and by this time we're going to oxygen. So oxygen is here, and oxygen has a molecular weight of 31.999. 32.00 is fine. Since our only measured portion here has 4 significant figure, you can use 32.00 grams. But if you wanted to use even more accuracy, you could. Well, if you had something more accurate here, you could use this. Okay, so it's the same thing. We are doing grams to grams. So we have 42.76 grams of C4H10 times 1 mole of C4H10 divided by that 58.123 grams of C4H10. Next is the mole to mole conversion. We are going from oxygen, so we have 13 moles of oxygen divided by 2 moles of C4H10. And finally, converting to grams of oxygen by multiplying by 31.9998 grams of O2 divided by 1 mole of O2. And the answer is 153.016 grams of O2. That's the answer to this question. Here it is all worked out neatly. Practice those, and don't always practice on grams to grams. Pay attention to does it say moles, because then you cut out a step, or just always pay attention to the units. We're going to look at limiting reagents, right? Now, if you are careful and you conduct a reaction, or you do a reaction in the lab, you can carefully weigh out and calculate the reactants and make sure everything works out perfectly. But it's not always the case. Sometimes you have an excess of a certain reagent, or not enough of one, and so it is nicely here illustrated what a limiting reagent is, right? So if you have 4 different reagents, right? You're making hamburgers. You've got the buns, and you've got the patties, you've got some pickles, and you got some cheese, and you decide to put you have 1 bun, 1 patty, and 1 slice of cheese, and let's say 4 or 5, let's say 6 of these. So you want 6 of these, 1 of these, 1 of these, and 1 of these, 1 pair of these, right? So it's kind of like 2 slices plus 1 patty. It's a chemical reaction, makes hamburgers, right? Makes 1 hamburger. And so we have, I don't know, I didn't count, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 patties. We could make 10 burgers, right? And we have plenty of cheese, looks like here, so we can make maybe this even like 14 or 16, and we have plenty of pickles. But our limiting reagent is, if you don't have more than 3 buns, you can't make more than 3 hamburgers, no matter how many patties and pickles and ketchup and whatnot you have. So you get the idea. That's a limiting reagent, and that you have to determine by calculating what that is. And so it's not as simple and straightforward as it is looking at patties and buns, right? So you have to actually look at the number of moles, yeah, and the stoichiometry, the balanced equation. So here we have a reaction, silver nitrate and copper, forming copper nitrate and silver, and this is balanced for you already, and so this is a 2-to-1 ratio. And the question is a vessel containing 1.256 grams of silver nitrate and 0.81 grams of copper react to completion. Which reactant is the limiting reagent? Now there's a number of ways to do this. We're given an amount. We're not given moles. If I was given, okay, we have 2 moles of silver nitrate and 2 moles of copper, then you would know that the silver nitrate is your limiting reagent, right? You do need, for every 1 mole of copper, you need 2 moles of silver nitrate. And so if you have 2 moles of copper, in order for all of the copper to react, you would need 4 moles of copper. So that's really easy to look at, right? But if you're given grams, you're going to have to do a little bit better than that, right? So if you wanted to do this, so first of all, what we're going to do is we're going to look at and write down the molecular weights of these reagents so we can convert grams to moles. So copper, straight from the periodic table, is 63.546 grams. Silver nitrate, if I calculate it, is 169.873 grams of silver nitrate. Okay, so those are the molecular weights, and so now my first step is to say, okay, so I have 1.256 grams of silver nitrate, AgNO3. I'm going to convert that to moles, times 1 mole of AgNO3 divided by 169.873 grams. Now, what I do, and so our next step would be to convert moles to moles, but I'm going to look at the moles of silver nitrate per reaction. That can also be a conversion factor. So one reaction requires 2 moles of silver nitrate, 2 moles of AgNO3. And I get a number here, and I forgot what it is. It's 4.42 times 10 to the minus 3 reactions. I'm going to read RXN, I think. Okay, and so I'm going to do the same thing for copper. I have 0.281 grams of copper times 1 mole of copper divided by 63.546 grams of copper, again times 1 reaction and 1 Cu. And so that gives me 3.69 times 10 to the negative 3. So copper is my limiting reagent. See, I have less copper than I do silver nitrate. And I couldn't have predicted that by looking just at the masses. I have to do this reaction. So here it is all neatly worked out the way I've shown you. And there's another way to do this. This is the shorter and easiest way to do this. But you could actually just pick a reagent and calculate, well, let's just do a gram-to-gram conversion all the way to silver. I can do it for copper and I can do it for silver nitrate. I take it all the way to grams of silver, and then whichever one is lowest is going to be my limiting reagent. But it really is easier not to do that. But anyway, you pick the lowest one here. 3.697 times 10 to the minus 3 is less than 4.42, right? Okay. So you can also do it where instead of going one reaction here, hang on, I got it. Select my pen real quick. Okay, right? So instead of putting one reactant here or one reaction, I just use silver, right? And so that actually works out well. And so here you see if you used these quantities, you would produce only 0.798 grams of silver because silver nitrate is the limiting reagent. Okay. So another example is same idea. A vessel containing 16.7 grams of butane, one of the reactants, and 66 grams of oxygen, the other reactant. Which reactant is the limiting reagent? You would set it up the same way. I'm not going to write it out. I'm going to pull up the solution here and show you. It's just like you have to convert the grams of the reactant, grams of butane, using the molecular weight, to moles, and then you do one reaction and you use the coefficient from the balanced equation. That gives you 0.14 reactions in this case. You do the same thing for the grams of oxygen, 66.9 grams of O2, convert to moles using the molecular weight and dividing by the coefficient here. One reaction you can do if you have 13 moles of O2, you can complete one reaction. That's all that means. And so the limiting reagent in this case is, and I have that, no, I don't have it circled in red, but it is 0.14. Taking this one step further, you not really a step further, but adding on something here. There's a limiting reagent and there's a theoretical yield, right? So then based on your limiting reagent, you can calculate the maximum amount of a product produced. And then in real life, you don't always make 100%. If you are working at a chemical factory that makes product X, then you know you may only have an efficiency that produces 80% at max. So you can calculate a percent yield here, and the percent yield is first you calculate the theoretical yield. How much can I possibly produce with reagent A and B, but how much did I actually get? So you measure out, you know, so in theory you were supposed to get 100 grams, but you only got 80 grams, so that's an 80% yield, not 100%. That's what percent yield is. It's no different than any kind of percent. And so again, I'm not going to write. I'm just going to show you, bring up and explain. Reaction begins with 47 grams of butane, an excess of oxygen, so we don't have to worry about the limiting reagents. We're only giving one reagent. So I set up my equation based on the 47 grams of butane. Okay, in the laboratory, the reaction produced 122 grams of carbon dioxide. So that's our product. So my first step is going to be the grams of butane to the grams of carbon dioxide, just like we did before. And so you set it up in the same way. You go from grams to moles of butane, from moles of butane to moles of carbon dioxide, and then from moles of carbon dioxide to grams of carbon dioxide. You get a theoretical yield, and then I'll tell you that this is what we actually produce. So then you just take that and you divide it by the theoretical yield, multiply it by 100, and so your percent yield in this case is 47%. We can do this all day long. Let's play around and have some fun, right? The more the better. Again, I suggest that you pause, work this out, and then look up the answer. Ammonia can be synthesized by the reaction below. It's already balanced for you. Here we can have NO and hydrogen gas forming ammonia. This is ammonia. Starting with 86.3 grams of NO and 25.6 grams of H2, find the theoretical yield of ammonia. Since I am given now two reagents, I have to find out what the limiting reagent is, and then I need to take that limiting reagent and calculate it all the way out to ammonia. Okay, now in this case you may be better off doing two separate calculations calculating the grams of ammonia that are produced and then picking the one that's less. Okay, so let's see what I actually did. And I did that. Okay, so I took the grams of NO and took it all the way to grams of NH3. And this is the fudge factory again, right? Grams of NO to moles of NO using the molecular weight, moles of NO to moles of ammonia using the stoichiometry here, 2 to 2 or 1 to 1, and then finally the grams of ammonia. So if NO, nitrogen monoxide, was the limiting reagent, then 48.9 grams would be produced. And that is true because if I do the same calculation with 25.6 grams here, doing the same thing, grams to mole using appropriate conversion factors, moles to moles, see there's a 5 now from the H2, and then grams of ammonia produced. So the limiting reagent is NO, and the theoretical yield is 87.04 grams. And you can't just say that, 25.6 is less, therefore it's probably the limiting reagent. No, it's not. It's actually NO, and we have 3 times as much, more than 3 times more mass. So you have to look at the mole-to-mole ratios, the molecular weights, and the stoichiometry of the reaction. So this is not that straightforward. You have to make those calculations. Again, the theoretical yield in this case is 48.9 grams. If I take that one step further and ask you for a theoretical yield, right? The reaction was performed under the conditions described with, 80, whatever it was, 86.3 grams of NO and 25.6 grams. So we use this theoretical yield here. And then all you have to do is take this actual yield divided by the theoretical yield we calculated earlier, and I have a typo here, right? So this was not a, this was, whoa, this is weird. This was 48.64 grams max, right? Gives me a 70.8% yield. Okay. One more, right? And this is just to point out this. I didn't balance this here, right? So this is something I've done for you so far. You should also understand that that's the one thing you want to check. So this is not balanced. So that's the first thing you want to do. Balance that thing so you can get your mole to mole conversions. Now the question here is hydrogen sulfide released during petroleum refinement can be trapped by reacting with oxygen. How many grams of sulfur are formed from 2,500 grams, 40 grams of hydrogen sulfide. Okay, so we have hydrogen sulfide, and I want to know how many grams of sulfur are formed. Okay, so we have this reagent going to that product. And then I go simply like I would, it's a gram to gram conversion from the periodic table, from the balanced equation. Again, from the periodic table, I get 2390 grams, 3 significant figures, 2,390 grams of sulfur. Maybe one more. Hydrogen bromide can be made by the reaction of sodium bromide with phosphoric acid. Shown there, this is balanced. How many grams of phosphoric acid are needed to make 39 grams of HBr? Grams to grams again, same thing. Not going to really explain it to you because it's all the same over and over. Now this one here is just slightly different, and I've been asking a lot of gram to gram conversions, but here I'm asking for moles. So you got to really pay attention. Grams or moles, right? So this is just going to be a two-step conversion. I am given grams of sodium phosphate, so you have to convert grams to moles and then moles to moles, and you're done. Right? So here you have the grams converted to moles and then moles to moles, and that's all I'm asking for here, right? Oh, well, why not one more? Well, I don't know. I tell you why not, because I'm tired and you're tired, and you can work this yourself. So, chapter 8 is next.